wandering domains in transcendental dynamics.
Right.
Please.
Thank you very much. It's a great pleasure to continue this tradition of coming to Będlewo in summer, and I hope it continues for many years. And I want to thank the rest of the organizers for letting me give this talk. Okay, so let me see if I can manage to do Lasse's homework and try to fill in the things that were missing in his talk. Okay, so these two talks are from the same paper actually, but I hope you will see like the different type of approach. We started, as Lasse said, this project, trying to solve things about wandering domains, and only at the very end of the project, we realized that the examples that we had been constructing were actually would give quite easily counterexamples to Eremenko's conjecture. Okay, so let me try to convince you. So this is basically a survey of results about wandering domains in transcendental dynamics. And let's see if I can make the case for why wandering domains should be your favorite Fatou components. Okay, so Lasse already mentioned that for transcendental entire functions, we have the same definitions of the Fatou set and the Julia set that you have for rational maps. And Fatou components can be one of these three types. Either they are periodic, so after n iterates, it goes back to the same Fatou component, pre-periodic, or wandering domains are just Fatou components that are not eventually periodic. So here we have explicit example of this type of Fatou component. So in this case, here we have that these black sets are invariant basins of attraction, but for this function here. But if you modify the function, which is periodic, and you add to pi, then instead of having invariant basins of attraction, each of these sets moves one step to the right. Doesn't want to move. Let's see. Okay. And then with the 2 pi added, this becomes an explicit example of an entire function with a wandering domain that escapes to infinity by translating exactly 2 pi to the right at each step. So at the time that Fatou and Julia started this theory, none of them knew whether Fatou components would be all eventually periodic, or there could be this possibility of wandering domains. The first person to prove that this could happen was Baker. And in fact, this theorem has a nice story. So Baker constructed this function in 1963, I think. And he knew that it contained a set that would go to infinity. But at the time, he wouldn't know whether these sets going to infinity, they would be part of the same Fatou component, or they would be in different Fatou components. And it took more than 10 years for him to prove that they were wandering domains. Each of these sets was in a different Fatou component. It is well known also that for rational functions, there are no wandering domains, at least in one complex dimension, because there is this result that there are skew products in C2 that can, polynomial skew products that can have wandering domains. Okay, Lasse already did this part. So we have this classification of points into the Fatou set and the Julia set. But then we have this other classification in terms of where orbits accumulate. So points may be in the escaping set if the orbit accumulates only at infinity. They may be in the set of bounded orbits if they're contained in a compact set. Or they may be none of these things. So if we were iterating a polynomial, these would be the only two cases we would have. Either you're bounded or you go to infinity. But for transcendental entire functions, you may go arbitrarily close to infinity and then go back to a bounded part, go to infinity again, and keep returning. And this is what we call oscillating orbits or Banji orbits. And then by normality, if you have a Fatou component that meets one of these sets, then the whole Fatou component needs to be contained in it. So we can talk about escaping wandering domains, bounded orbit wandering domains, and possibly oscillating wandering domains. These bounded orbit ones, there are no examples yet, if they exist. Okay. Also, another So Baker's example actually of a wandering domain, it was multiply connected. So it looks something like this. So you would have like some annulus, possibly with some poles, which maps to larger annulus. This maps to a larger annulus. That's right, and points would go to infinity in this sort of complicated shape a priori, but in fact, it's much more simpler than the simply connected case. And actually, whenever, this is not only multiply connected wandering domain, so whenever you have a multiply connected Fatou component, actually it needs to be a wandering domain and it needs to be of this same type of dynamic. So every multiply connected Fatou component is actually an escaping wandering domain and has the same properties as Baker's original example of a wandering domain. And as I said, like part of the point of the talk is to say that these things look complicated, right? You saw the simply connected example before. These a priori, they look more complicated, but in fact, in terms of their topology and their dynamics, they are much more simpler to understand than simply connected wandering domains, although it's a bit counterintuitive. Okay, so I wanted to give a list of different examples. This is not an exhaustive list in any way, but I tried to choose some examples that can represent the different things that can happen. So the first one is the first example that I was talking of Baker, where you have a multiply connected wandering domain that escapes to infinity. Then Herman gave this is the function that was the picture was in the slides before, which gives us the first simply connected wandering domain. Then Eremenko and Lubitsch had the first oscillating wandering domains. And then also within multiply connected wandering domains, Kisaka and Shishikura showed that they can have different eventual connectivity. So it can be eventually two or eventually infinitely connected. And finally, I wanted to mention Bishop's example, which was the first example of a wandering domain in class B. So in the class B, you cannot have escaping wandering domains. And for a long time, it was not known whether you could have any wandering domain at all, because functions in the class S cannot have wandering domains. And people were wondering whether functions in the class B would be similar to functions in the class S, or whether they could have wandering domains, and they can indeed have them. Also, I chose these examples because they also show that wandering domains can be constructed in many different ways. So you can have examples by doing infinite products. Also, Herman championed this thing of creating a function in C star and then considering the lift. And then the lift of an invariant component in C star then becomes in C a wandering domain. They can be done by approximation theory. These ones were done by quasi-conformal surgery, and more recently, quasi-conformal folding. So there is a huge variety of ways to do wandering domains. Also, wandering domains, in my opinion, they are important in transcendental dynamics, not only on their own, but also because they are related to many of the main problems in transcendental dynamics in some way or another. So for example, in 2018, Bishop gave the first example of a transcendental entire function whose Julia set has dimension 1. Often transcendental functions have Julia sets of large Hausdorff dimension, often 2. So this was the first example of dimension 1. And this function has one of these multiply connected wandering domains. And so far, we don't know how to obtain this without using wandering domains. Another example is this problem about commuting functions. So whenever you have two transcendental entire functions that commute, is it true that the Julia set of these functions is the same? So there has been a sequence of results in this direction. First, it was for functions with no escaping Fatou components, then for functions with no fast escaping Fatou components, then functions with not. The last iteration of this is 2016 by Anna-Miriam Benini, Phil Rippon, and Gwyneth Stallard. And it says that if the functions have not fast escaping simply connected wandering domains, then this is true. So this shows that it's kind of like we lack some understanding of how bad simply connected wandering domains can be. And finally, this is the result that Lasse was talking about. We use wandering domains in connection to constructing a counterexample of Eremenko's conjecture, like that. Okay. Are there any questions up to now? No? Okay. So the structure of the talk is as follows. There are two parts. One, the first half is about the topology of wandering domains, and the second part is about the dynamics on wandering domains. So our first motivating question for the topology part will be, which open sets can arise as wandering domains of transcendental entire functions, right? This is a very basic question that also, like, now it makes sense, but if you asked me 3 years ago whether we could say something about this, I would have said it would be impossible, but now we have a very good understanding of this. Okay, so in principle, one would not expect that you can get everything that you want because, for example, in the case of polynomials and invariant Fatou components, there is this result that was already mentioned a couple of times during the conference. There's this result, nice result by Anya, saying that whenever you have a polynomial and an invariant basin of attraction, then there is this dichotomy that either the boundary is an analytic curve or it has Hausdorff dimension strictly larger than 1, so it cannot be any set. And for this analytic curve, these are either you have a circle, if you have like z square, or you could have like an arc of a circle, for example, if you have z square minus 2, would be an interval. So in principle, one would not expect to have anything that you want. A related question was this one posed by Fatou in 1920. He asked this in a paper about rational functions. He asked, if you have a function that has more than 2 Fatou components, and hence it has infinitely many Fatou components, can 2 of these share the same boundary? Okay. So in fact, this question is still open in the context of rational functions, but 6 years after this paper, Fatou started studying transcendental entire functions as well in I think you cannot see it, but 1926. And we think that this question probably would make sense also in that context. But yeah, that's the one that we will solve. So one very strong situation in which this sort of behavior happens, that you have 2 Fatou components exactly with the same boundary, is when you have what is known as Lakes of Wada. So for those that have not seen this, I will explain this topological construction quickly. So imagine that you have a domain in the plane, like this black set here, which you can think of as an island. And this island has 2 lakes, which have disjoint closures. And if you're living in the central part of the island, it would be quite tiring to walk every day to this. The white set outside plays the role of like the sea around the island. So it would be very tiring to walk every day to the sea to collect some water. So you may decide to put some effort and build a canal that brings the water near your house rather than you going to fetch the water every day. And then you could, let's say like the next year you get more demanding or more lazy, and you want to construct more canals that bring each point from the lakes and from the sea closer to every point in the island. So you can construct this sequence of canals, right, that have the property that they never disconnect the black set. So the black set is always connected, and the distance from each of the black points to each of the canals decreases as you go along the sequence. So you can keep making this operation, and in the limit, what would happen is that you would have no remaining black set. So the black set would have no interior anymore, but it would instead be the boundary between the white, the dark gray, and the light gray lake. So this is a more realistic picture of this situation. In here, what you're seeing is like 3 bounded domains on the plane, a blue domain, a yellow domain, and a black domain. that are bounded and the white domain that is unbounded. So these are 4 domains that have exactly the same boundary. Yes. Okay. So Lakes of Wada are exactly this. So they are Lakes of Wada continua, sorry, are continuum that satisfy that they are the boundary of at least 3 disjoint simply connected domains. The existence of Lakes of Wada continua was proved by Brouwer in 1910. And you may even have infinitely many lakes sharing the same boundary. That's no problem. Here you have a picture from Brouwer's paper about how he imagined this collection of domains sharing the same boundary. But these are called Lakes of Wada domains because around the same time there was a paper by a Japanese mathematician called Yonoyama, which had this sketch in his paper about how to construct this situation. So here you can see that he drew the island, the land, and one lake, and the canal that goes around. So in this situation, we wouldn't call this a Lakes of Wada continuum because there's only like one lake and one sea. So for us, a Lakes of Wada continuum need to bound 3 different sets on the plane. But and he attributed this to his PhD supervisor called Wada, which is this person here. And we got this picture from Yutaka Ishii that got it also from the mathematics library in Kyoto University. There are not so many. So for some time we didn't know much about him, and then we received this email from Yutaka Ishii with this picture, and we were very happy. Okay, so you may be thinking now that Lakes of Wada look very pathological in a sense, right? Like they look strange if you have not encountered them before, but actually in the study of dynamical systems, there are many instances where they appear. So for example, there are perturbations of anosoptic meromorphisms of the torus. So this is the Plikin attractor, which is the same figure that you've seen before. It's the same attractor. Also force pendulums, Enon maps in R2, etc. But before this work, there was no example of Lakes of Wada appearing in one-dimensional complex dynamics. So just to go back to remind you of what Fatou's question was, he asked when you have 2 Fatou components, can they have the same boundary? And what we proved is that there exists a transcendental entire function with a bounded Fatou component whose boundary is a Lakes of Wada continuum. In fact, what we show is that this function has infinitely many bounded wandering domains, all of which share the same boundary. It's quite a strong way to answer this in the transcendental case. So this result was very much inspired by work by Boc Thaler that he did in the beginning of 2021. So he proved this type of result. He said, if U is a bounded simply connected domain such that 2 conditions happen, so you need to have that one is that U is regular, and the second one is that C minus U is connected. Okay, he said if you have these 2 conditions, then there is a function for which U is a wandering domain, transcendental entire function. Okay, so regular means that when you take the closure of the domain and then the interior again, you recover the original domain. So something like a disk with a slit would not be a regular domain. So when you take the closure, you get the closed unit disk, and then the interior is the open unit disk, which is not the same as the starting thing. Then an example of a domain with whose the complement of the closure is disconnected could be this. So the dark gray set here is a simply connected set, but when you take the closure and look at the complement, it has this bounded part and this unbounded part. So this would not be something that satisfies this theorem. But besides these 2 conditions, you could get it. He also proved that the condition of being regular is necessary, and he asked whether Fatou components can actually have this situation. Whether Fatou components, if you have, he asked if the closure of any bounded simply connected Fatou component necessarily has a connected complement. whether this can happen or not. And our Lakes of Wada example satisfies this, because when you take the closure and look at the complement of one of the lakes, in particular, it contains each of the other lakes that share the same boundary. So we answer this question. And in fact, this example is a particular case of a more general theorem that lets us construct wandering compact sets. And it says the following: if you have a full compact set K, so full means that it has no bounded complementary components, then we show that there is an entire function for which the boundary of K is in the Julia set. K is what we call a wandering compact set. So this is the version of, it's like a wandering domain, but a version for compact sets. Then every connected component of the interior will be a wandering domain. This follows from this. And on this set, the function converges to infinity. So you get an escaping one, okay? So using this, we can construct this Lakes of Wada example. And then in case you're wondering, so there is still more room for working in this direction, because we still don't know exactly what are all possible wandering domains, bounded wandering domains, simply connected for entire function. So we don't know. So this is the updated version of Boc Thaler's question. So now we don't know if you can have a bounded simply connected Fatou component such that it has a disconnected complement. The closure has a disconnected complement, but it does not satisfy this condition. So all the ones that we construct satisfy that the boundary of the field of the closure equals the boundary of the domain itself, like in the Lakes of Wada case, because we use this in the construction. Okay, so I'm gonna briefly sketch the construction in 5 minutes. So in this construction, as Lasse said, we obtain the resulting transcendental entire functions as a limit of a sequence of transcendental entire functions, such that each function is closer and closer to the previous one, so that they converge to some limit. And each of the functions in the sequence is obtained, in this case, by using Runge's theorem. So Lasse said before that in his construction, he used Heraclian's theorem, because we may have, in that case, unbounded sets where you want to approximate. But in this construction, it's enough to have a bounded compact set each time. Of course, the union of these compact sets, it gets larger and larger. And at the end, the union is the whole plane, but that's okay. Okay, so what we do is like our ingredient. So we start with a full compact set. So we have the full compact set, and then we can obtain for each compact set, in this case, do this rabbit, we can obtain a nested sequence of compact sets such that their intersection is our starting compact set. And then we can choose also a sequence of points in these sets here. So in the light gray sets, we can choose a sequence of points, one in each set, with the property that this sequence of points accumulates exactly at the boundary of the compact set that we want to become a wandering compact set. So we start with a compact set, okay, in black here. Then we obtain this nested sequence of compact sets whose intersection is K. And then we produce a sequence of points, one contained in each of these sets, with the property that their limit, their accumulation set of this sequence is exactly the boundary of the set K. Then what we do is we start constructing first a function that satisfies, that maps a disk inside itself, okay? And one point, the first point P1, the first point P1, okay, maps also inside here. And at this point, you need to observe that once you construct this sort of function using Runge, every function that is sufficiently close to this function will satisfy the same properties. So if D1 maps well inside itself, if you perturb it with epsilon, it will still be contained in itself. So D minus 1 will still be a basin of attraction. And hence, P1 will also be contained in a preimage of this basin of attraction. And then so we map this point here, and we map this set to the right by Z plus 1. Then in the next step, what we do is we want a function that, so we apply, so we obtain a first function F1, say, that has these properties that I drew here in blue. And then in the next step, the next model map will be whatever is inside this this disk delta 1, and then we prescribe new things outside. So at the second step, we want to be close to whatever we achieved before inside delta 1, and then add the properties that this point here, which is the one that came from P2, we don't know exactly where it is, but it's F1 of P2. So we want this point to be mapped to the basin, and the next step to move 1 unit to the right. So now we know that this point will be in a preimage of this basin of attraction. So this starting point here will also be in a preimage, like a second preimage of a basin of attraction. And then again, like in the next step, we preserve what we had until now, and then prescribe things inside D2. And if we are careful and we make these epsilons become smaller and smaller, we can make all these properties to be preserved at the same time and converts to a function that has here inside D0, where K lives, the sequence of points that accumulates to the boundary of K. Hence, the boundary of K is a point is a subset of the Julia set. And the interior of K is necessarily a wandering domain because on the interior of K, the dynamics is that you move to the right by translation by 1 plus epsilon at each step. Okay. This is my brief sketch of how the proof goes. Are there any questions until here about this construction? No? Okay, so now I want to talk about meromorphic functions. So what can we say about the same question but for meromorphic functions? So I want to take U to be a subset of C, to be open, connected, and bounded. First of all, let me say that for meromorphic functions, you have the same definition of the Fatou set and the Julia set, with the exception that for the Fatou set, you need to require that the iterates are defined on those sets of points. But apart from adding this red thing, you can have the same definition. So if you have an open, connected, and bounded subset of C, you can ask what conditions it needs to satisfy so that it exists a function meromorphic such that U is a Fatou component. So what are the conditions that open sets need to satisfy? So that they are Fatou components of some meromorphic function. Are there any ideas if you have not seen this talk in the past? Do you know of any condition that is required, at least, to have U being a Fatou component of a meromorphic function? Okay, so for example, before I was telling you like, right, you can have, so this is an open, simply connected domain, right? But it is not, so a Fatou component cannot look like this. Okay. So So for sure, you need to have that U is regular in order for it to be a Fatou component. And in fact, the surprising thing is that for meromorphic functions, this is enough. There is no other condition that we need to impose, and we have a full characterization of bounded, which bounded domains are Fatou components of meromorphic functions. Right? This is the theorem, right? So now imagine that we want to talk now about bounded components of the Julia set. So I will modify this. I'll call them X. Maybe not visible. Okay. X, not open, closed. Okay. Such that X is a Julia component. So a Julia component is just a component of the Julia set. So what are the conditions that such closed, connected, and bounded set needs to satisfy to be a component of the Julia set? Any ideas? Maybe someone online has ideas. People here don't seem to have. Okay, so I'll tell you the answer. So okay. So the answer is that it is enough to ask that X has empty interior. Okay. So for example, so if you have any continuum, so bounded, connected, closed set, then the fact that X has empty interior is equivalent to the fact that it's a Julia component of a meromorphic function. Here you have 3 examples of such continua. So it means that for each of these 3, you can have a meromorphic function for which these sets are exactly a component of the Julia set. So you can have a meromorphic function for which the boundary of the Mandelbrot set appears on the dynamical plane as exactly one of the components of the Julia set of this function, which I think is nice. Okay. Maybe enough of topology. Let's go back to dynamics. Any questions so far? Okay. So in terms of dynamics, there are 2 kinds of dynamics that I want to discuss. So you could have, because we already said that there is a first classification of dynamics on wandering domains. Oops, not this. Here. In terms of like whether they are escaping, bounded orbit, or oscillating. This is like a first classification. But then you can do further than that and look at 2 other things. One of them is what are the internal dynamics. So if you forgot that this component is wandering around and you rescale it back to the same place, kind of, what are the dynamics within the set? Do points converge to the boundary? So Benini, F. Doridou, Fagella, Ripon, and Stallard used inner functions to study this problem for simply connected wandering domains of entire functions. And they looked at 2 quantities. First is that if you take 2 points in the domain and look at their iterates, what's the relationship between them? Do they get closer to each other? Do they stay the same distance? And this gave rise to 3 cases, this contracting, semi-contracting, or eventually isometric cases. I don't want to enter too much detail. Another thing that you can look in terms of internal dynamics is what is the relationship of the orbits with respect to the orbit on the boundary. Do points converge to the boundary? Do they stay away from the boundary? They can also be bungee, which is like they go close to the boundary in some steps and then go away from the boundary in other steps. And each of these 2 conditions in their paper had 3 cases. So it gave rise to 9 cases. And they were able to realize these 9 cases in the case of escaping and 6 cases in the case of oscillating. So this is one thing. Also for multiply connected wandering domains, the situation is so much easier because they are all escaping, and in fact they are fast escaping. And moreover, Bergweiler, Rippon, and Thaler proved that they contain large annuli that are absorbing. So every orbit at the end will be contained eventually in one of these large annuli that you can have some formulas and some estimates about what modulus they have. So they have very simple dynamics in a sense. Okay, so I need to do the homework. I've been escaping a bit. Okay, so we have these maverick points that Lasse introduced. So when you have a transcendental entire function with a wandering domain, we say that a point in the boundary is a maverick point if there is a sequence of iterates where the orbit of Z tends to some point W in the Riemann sphere, but W is not a limit function or a limit of the corresponding iterates on the domain U. In other words, the points in U are going to some place, and this point in the boundary along this sequence is always tending to a different limit. This is why they are called maverick points, because they are kind of like independent and they do different things. So as I said, I don't know if I said this before, but so multiply connected wandering domains are fast escaping, actually. And this means that their boundaries in particular, they are also fast escaping. So in the multiply connected case, all points in the boundary do the same as what points in the wandering domain do. So there is no maverick point in that case. Also, why we call them maverick also is because most points don't do like that. So Rippon and Thaler proved that for escaping wandering domain, with respect to harmonic measure, most points are escaping if U is escaping. So the set of non-escaping points in the boundary has harmonic measure 0, although there was no example of this. Then Osborne and Sixsmith did a version of this for oscillating points. One comment I want to give here, let me try to go back, is that if the wandering domain is escaping, so the limit function, the only limit function is infinity, this means that every point in the boundary that has a finite accumulation point is a maverick point of an escaping wandering domain. However, if you have an oscillating wandering domain, say that it accumulates to 0 and to infinity, okay, then you can have maverick points that they even have the same accumulation set. You can have points in the boundary that accumulate also to 0 and infinity. However, they do so at different times. So it's not only about the set, but it's only about at which sequence you're accumulating to these points. Okay. So they studied these sorts of points. But so far, this is the most general result, which covers, because they didn't have this notion of maverick point where they proved this. So this is the more general result, which covers most of the oscillating cases that were not covered here, actually. So we proved that for a transcendental function and a wandering domain U of F, the set of maverick points has harmonic measure 0 with respect to the boundary. Okay, so Lasse also mentioned Phil's question. Like he asked, if you have an entire function and U is a bounded escaping wandering domain, does the boundary of U need to be escaping? In other words, can you have maverick points in the case of escaping wandering domains? So far, there was no example of this. And we managed to show that, yes, you can have them, and you can actually have quite a lot of them. So this set of maverick points, which is small in terms of harmonic measure, is not so small in other senses. So we can have examples of escaping or oscillating wandering domains with sets of maverick points that contain continua of positive Lebesgue measure. So in terms of Lebesgue measure, it's not that small, but in terms of harmonic measure, still have harmonic measure 0. We also have this more general version of our result that I showed you before. If you remember, what I discussed before is you have a compact set K, and you can make it an escaping wandering domain, wandering compact set, and each of the interior components can become an escaping wandering domain. This finer version of this result says you start with a full compact set, but now you prescribe you're allowed to prescribe two sequences of points on K such that they can be infinite sequence, such that you cannot have 2 points in the same interior component from different sets, because if an interior component is escaping, it cannot have an oscillating point, etc. And then at the end, you obtain the same result, but you achieve to have this sequence Zi to be escaping points and this sequence ZBU to be oscillating points. So if you imagine in the case of Lakes of Wada, you have these infinitely many bounded wandering domains that all share the same boundary. You can, in each of them, pick a point and tell this point I want it to be escaping. This one I want it to accumulate to this set of points. This one I want to accumulate to this other set of points. So you can make that every lake has different dynamics. So from respect of when you are inside one of the lakes, all the points that you see around you in terms of harmonic measure, they behave similar to you. But then when you change, of course, the boundary is kind of bigger. So when you change to another one, this set becomes small, well, harmonic measure 0, and then another set of points, subset of the boundary, becomes relevant to you in terms of harmonic measure. And this is what is happening here. So just to summarize, I wanted to say that I think wandering domains are nice Fatou components that can be constructed with a wide range of techniques and that are related to many problems in transcendental dynamics. Also, this point that I made before, that simply connected wandering domains, which 5 years ago we always thought they would be simpler than multiply connected wandering domains. Now we kind of switch and we think that these are really the complicated ones to understand, and there are some remaining cases that we have very little idea on how to understand. Then that for meromorphic functions, we have this complete characterization of which bounded sets are Fatou components or wandering domains, and which bounded sets are components of the Julia set. So this problem is solved for meromorphic functions, but we still don't know the answer completely for entire functions. And that this set of maverick points, there are a lot of questions that remain open, and hopefully in the next years we will be able to say a bit more about that. Okay, I'll stop here. Thank you.
Very much. Any questions?
Thank you, David, for a nice talk. I was wondering about this Fatou conjecture, or Fatou question about rational functions. What is the state of the art, and what do people believe in about two Fatou components sharing the same boundary?
Yeah, I don't know. It's also related to Makienko's conjecture. Yeah, I don't know. I don't work in rational functions, unfortunately. I'm not sure what people, experts in rational functions, know. But since there are a few in this conference, you can ask them. Lasse, can you?
Well, as we heard yesterday
Yes,
from
for
Dima, for quadratic polynomials, we now know that this does not happen, right? So the question was remaining whether this could happen for Ziegler disks, and we now know that's not the case due to his very, very deep work with Michal Ljubich. I think in general, I don't know, Dima might say, but I guess we probably think in general it doesn't happen for rational maps that you get these Lakes of Wada, but you guess it's not. Okay.
Any other questions or comments? Okay, so maybe we should go and have a coffee break, and then we meet at 20 past, I assume.